Energy is liberated matter. Matter is energy waiting to happen.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Matt, Bill Bryson, one of my mum's favourite authors ever, and she introduced him to me, not physically. She lent me some books when I was very young, and I love Bill Bryson. What a great writer.
Really great writer, and has done some very excellent science books as well.
Yes, he's not just a funny man. He also knows his stuff.
He knows how to be a science educator.
You sounded like that guy who says he straps money to his thighs.
I hope you don't. Yeah, I know.
Yeah, horrid. Matt, on this day,
yes,
7th of February, 1984.
Let me guess what you're going to say, Jamie.
What do you think?
Because it's such an iconic photo of a spaceman floating on his own, untethered,
Yes,
on a spacewalk. Bruce McCandless II and Robert L. Stewart made the first untethered spacewalk. And what they're wearing is the MMU.
What, the manned manoeuvring unit?
The manned manoeuvring unit, which in the film Gravity, where Clooney is basically messing around, not very realistic. It would be highly dangerous to be so frivolous, considering one false button press would send you into the darkness of space, never to be recovered.
It would.
So it's a dangerous thing. So they don't often do it, but it definitely is one of the most iconic pictures of all time, isn't it, that?
It is absolutely incredible. And today's a great day, Matt, because we've got a happy birthday to one of our favourite guests ever, a very early guest on the show, Mr. Alfred Worden. Al Worden.
How cool is that?
Happy birthday, mate. I hope you're eating spaghetti and a nice glass of vodka.
To wash it all down. He's not the only astronaut. There's Heidemarie Martha Stefanshin Pipe.
Oh, wow.
2-time space shuttle astronaut.
Happy birthday. Matt, if I know you, and I think I do, you've probably got some sick space news for me.
I did. I stayed up last night,
Yeah.
quite late, writing the podcast notes. And as you know, we're recording on a Friday and going to try and get it out in a few minutes.
Ooh.
So let's not make this a rambling one, because we're late, because we've both been busy. But yes, I stayed up and watched the UK-based OneWeb company launch 34 satellites from Baikonur on the Soyuz with a Frigate M, not quite our favourite upper stage there. They want to have their rival to Elon Musk's Starlink operating by the end of 2021. So they're another company that are now going to be throwing up large amounts of satellites. So Starlink and OneWeb, and probably joined by a couple of other companies.
It's not really the sort of thing you want people to be competitors over, is it?
Well, you can't. No, I think.
Why don't they join forces, Matt? Way less satellites in space. Already thousands.
Jamie, I'm going to stop you there. I mean, just think of the problems that Sky, for example, having a monopoly over that kind of broadcast
Very true.
has had.
Very true.
I mean, you might actually put all of the world's problems down to that. So I think it is important that we have competition, but maybe we haven't really fully assessed the environmental impact.
This is what I'm
things.
concerned about, you see.
Yeah, I think we should have competition, but
maybe
it's not worked out very well. They're not the first people to try this, by the way. Other companies have gone to the wall. The early kind of attempts, because it's just so expensive.
Well, Matt, is there a limit? Unit. Is there a limit of the amount of satellites that you can put up in space as a company? There must be.
No, there appears not to be. I mean, bear in mind that Starlink is supposed to be something like 22,000 satellites. Well, clearly...
Well, it's ridiculous. I mean, if Musk went tomorrow, I'm going to put 1 million satellites up. What would someone... Could nobody do anything?
No, you need to get approval. You need to get approval from the Americans, actually, to actually stick satellites up, because you're going to be launching from America. So you basically have to have approval from wherever you're launching from. And of course, there's only a few places you can launch from because it's really difficult. It seems to be that Elon Musk hasn't had much problem getting approval. I think the rules need tightening up, Jamie. That's just my opinion.
Well, I think I agree with you.
Well, we're talking about SpaceX and their Starlink. Gwynne Shotwell, the company president and all-round awesome person who's keeping Elon Musk in check and making the whole thing work, I suspect, basically said, that particular piece is an element of the business that we are likely to spin out and go public. Right now, we are a private company, but Starlink is the right kind of business that we can go ahead and take public. So imagine how much money that thing's going to be worth. If it's working and they spin it out, then there's a whole heap of money for Elon Musk and SpaceX to go to Mars.
I was going to say, they won't need to go cap in hand as much. Wow.
In SpaceX rivalry terms, Boeing Starliner, we had that test right at the end of December.
Yeah.
And it didn't go well because it just didn't get to the International Space Station, the Starliner, unlike the kind of equivalent Dragon test. It apparently had some other really, really serious issues with the software that are only just coming out now. Like so bad that if they hadn't have uploaded some data during the descent, the spacecraft would have been lost.
Yes.
That sounds pretty bad. I mean, if you're the astronauts that are going to be flying on the Starliner, it's uncomfortable news, I would imagine that.
Yeah, that is uncomfortable news, isn't it? I mean...
when your life revolves around a software update.
Exactly.
I mean, I get I get angry enough as it is when I have a software update, let alone when my life is dependent on it.
Do you click on your computer that you're going to just do it tomorrow? I'm that guy.
Yes, I do. I do.
Remind me
on my
tomorrow.
Mac, I said, remind me tomorrow. Yeah, I definitely do that. Windows doesn't really give you my Windows just does it without me really knowing what's going on. But hey.
Yeah. Let's not get into that.
Oh, Jamie, one of my favourite pictures of the week, and it was an absolute corker, wasn't it? Christina Koch, as she's being pulled out of her little Soyuz capsule as she arrives back.
And you emailed it to me by accident, and I thought you just sent me a lovely photo to be a good friend. And then you said, wasn't meant to send that to you.
That classic thing of there's no easy way of getting it from your computer to your phone without emailing it. I just went through the easiest thing I could think of, and then I didn't realise that I was emailing it to you.
Well, if you had an iPhone, Matt, you could just airdrop it.
But then I did send you a lovely picture of Kirk Douglas and Farrah Fawcett.
That is true. And then we were friends instantly again.
Instant friends.
Yeah, it's brilliant.
So, we should say, poor old
rest
Kirk
in peace.
Douglas. Yeah, rest in peace. And if you haven't seen the film Saturn III, it's worth a watch. It's a British film, actually, written by Martin Amis, of all people, but it's quite strange. It's pretty wacky and out there.
Do it.
But it's Harvey Keitel, Kirk Douglas, Farrah Fawcett. You can't really go wrong with a cast like that, can you? Yeah, so Luca Parmitano and Alexander Skvortsov were also coming back in that particular capsule, and it's all gone very well. And so, yes, some people back on Earth.
There we go.
Some astronauts safely back on Earth. Well done.
Excellent stuff.
One last bit of news before we go on to our special, Jamie. I've decided to have a special as our interview fell through this week.
Yes.
Worrying. I don't know whether it's worrying, and I think this is certainly something that the Space Force will be involved in, I would imagine.
Yeah.
There's a Russian satellite that appears to be tracking one of the American spy satellites. You can actually look at the public data, or you could even get your telescope out and look at it doing it yourself. And that's Cosmos 2542. Is synchronizing its orbit with USA 245, which is widely believed to be one of these KH-11 spy satellites, which is essentially a Hubble telescope that's looking at the Earth, taking pictures of strategic places,
right,
like Iranian launch pads and stuff like that. Anyway, it looks like Cosmos 242 has released some inspection satellites that are now tracking this spy satellite and is really close. So it's pretty unclear what it's doing, but it's almost certainly, I don't know, filming the satellite or looking at its at where it's pointed or something like that. Maybe quite frightening. That sort of cat and mouse game is now happening in space, as well as with submarines and bombers and
it was only a matter of time.
Yeah.
Send in the Space Force.
So yes, that's the sort of thing I suppose the Space Force will have to deal with.
We're going to have to do it.
Space Force Strategic Command. Yes, we've also got ESA and NASA's Solar Orbiter being launched this week, which is going to be very exciting.
Get in.
Look out for that one, and we'll talk about Solar Orbiter probably next week because it's definitely worth talking about. Jamie.
Yeah?
I want to talk about dark matter.
Oh, finally.
Do you know why? Because there's a news story that I've been getting quite excited about, and I think I probably shouldn't be because it's probably wildly speculative.
Really? About space?
No, this is from a proper journal.
Oh.
And it's a really good paper from a professor in Portsmouth, but I'll get onto that in a second. First of all, we should really talk about what dark matter is and the kind of... Because I think a lot of people think that maybe it's just nonsense, but it's been around for a long time now. So when you look into space, you can't actually see most of the universe, and it's not because it's dark or it's hidden by clouds or it's not reflecting light. There's something else. We're blind, and embarrassingly, and of course this is really the biggest problem in cosmology, etc., that and the Hubble constant, is 85% of the universe, the mass of the universe, is not. We don't know what it is, and we can't even see it. And it's like So some of that is dark energy, and some of it is dark matter, and they're not the same. They're different things. Dark energy is to do with this Hubble constant and what's actually making the universe expand, this special energy. But dark matter is literally what it says. It's matter that seems to be so invisible, but we know it's there. We know it's there, even though we can't see it with any known instrument or touch it with our eyes or skin or fingers. We just can't touch it. We can't see it. So it doesn't interact with anything.
Stop trying to touch things with your eyes.
Well, sometimes you have to, because it's a very sensitive feeler, isn't it? Your eyeball.
Very true. Yeah.
Yeah, I often imagine going around trying to feel things with your eyeball. It'd be quite painful. So I think a really brilliant person to talk about in relation to this, and actually you probably don't hear about him in this context, is good old Lord Kelvin.
Ah, Lord Kelvin.
Lord Kelvin. William Thompson is his actual name, and he was born pretty much 200 years ago in Belfast. And he was inspired to go into science because he loved this poem by Alexander Pope. Do you want to hear it?
Sure.
Go, wondrous creature, mount where science guides. Go, measure earth, weigh air, and state the tides. Instruct the planets in what orbs to run. Correct old time and regulate the sun.
Do not adjust the speed of your digital device. That was Matt's Belfast accent impression. Very good, Matt.
Sorry,
very good.
Oh, was it all right? It's one of those things where sometimes it's all right and then sometimes it's not.
It's pretty good. Enjoyed that.
The weird thing, his work crosses over into the work that I want to talk about a little bit later quite a few times. There's quite a few connections, which is why I wanted to talk about Lord Kelvin, because he's actually so much better than I thought he was. I just genuinely thought he was one of these scientists who came up with a scale, know, the Kelvin scale, the one that we actually look at temperature. So his early work was precisely that. He was involved looking at the work of Carnot and Joule. And with Joule, he kind of disagreed with Joule at the beginning, but eventually him and Joule really lined up their view on things and pretty much laid down the groundwork for thermodynamics. And he even talked about things like the heat death of the universe. Yeah, that's how ahead of his time he was. And he realised that as you cooled down, you'd eventually get a state of no energy. Hence, the sort of 0 Kelvin is where there is literally no energy left. He was knighted. He became this Lord Kelvin because he was heavily involved in laying the great transatlantic cables. So the cables that go from Britain to America.
Wow.
And was heavily involved in data technology and the bandwidth of these particular cables, something that was a really novel concept. Information being sent by electricity down cables was an amazing concept. And we'll get onto this in a minute because it's really, really important. Even though he was a creationist, he thought that the universe followed the laws of thermodynamics as he understood them, and therefore was this dynamic system that it had come into being and was slowly following thermodynamics and changing, and that's what was governing how the universe was evolving. And he realised, of course, that everything must be cooling down. And so he even tried to show the age of the Earth. He was wildly out, but he was only wildly out because they didn't know about radioactive decay and therefore didn't know that there was another kind of heat source that people hadn't thought about. But yeah, so his work kind of coincided with Darwin's and stuff like this. So really, really important. And then he gave a lecture in 1900 that alluded to two dark clouds in physics, and that was the movement of matter through the ether and how the statistic temperature relating to energy systems might break down. He thought these were the two things that he could see were going to be a real big problem and already had become a problem. Like Mercury moving around the sun, for example, was a problem. We knew that there was that precession that just wasn't quite right. And both of those were solved by Einstein 5 years later in his Annus Mirabilis, which is, he basically wrote 4 papers that changed modern physics, including solving all of Kelvin's problems. But what he didn't know is that earlier he'd talked about another dark cloud. So in 1884, Kelvin had used the velocity of stars orbiting the galaxy, so around the Milky Way, and tried to determine the mass of the galaxy, and realised that the mass was far greater than that of visible stars. So this is what he said. He said, "Many of our stars, perhaps a great majority of them, may be dark bodies."
There we go, he's back.
Sort of almost like a throwaway sentence in a talk somewhere in 1884. And over 20 years later, and the year after this Einstein having his Annus Mirabilis, a guy called Henry Poincaré used the word dark matter, although actually he called it matière obscure.
Sounds cool.
While discussing this Kelvin's 1884 paper.
Yeah.
It's the first kind of people realising that there's lots of dark stuff out there. And then you've got the Dutch. The Dutch took over, and a titan of Dutch astronomy, a guy called Kapteyn, lots of work about galaxy rotation. And he hinted at the existence of dark matter in 1922. And just so you know how cool Kapteyn was, his son-in-law was Hertzsprung, and his grandchild was called Regal.
Bloody hell!
That's how cool. Yeah,
wow.
That's cool. And his mate Oort, obviously the Oort cloud named after him, in 1932 also used stellar velocities and basically was saying, look, there's lots of dark matter out there. But Swiss astrophysicist Zwicky also started showing this, and this whole movement starting to take hold. And he said there's enormous amounts of dunkel materia, which is dark matter in some dunkel materia. Enter one of the greatest astrophysicists of all time, and that's Vera Rubin in 1970. And with her, along with Kent Ford, they actually did the most accurate measurements of Andromeda and other spiral galaxies that are side on. And in their 1980 paper, pretty conclusively showed that galaxies contained about 6 times more matter than just the visible stars, and that it must be in this invisible form. So at this point, dark matter is basically recognised and has become this major unsolved problem in astronomy. And really, Vera Rubin and Kent Ford is one of the biggest Nobel snubs there is, I think.
Ridiculous.
So a lot of people are, saying that Vera Rubin should get this Nobel Prize. But, that's the way it is. And, if you're Richard Feynman, who gives a monkeys about the Nobel Prize? It's
Exactly.
actually more hassle than it's worth, in his opinion.
Yeah.
And that the great joy is that of finding out. So I hope Vera Rubin had that great joy of finding out. Of course, she died quite recently. Of course, the 80s, Jamie, was when we saw this huge explosion of, technological astronomy, which is carrying on today exponentially in spades. We are living in the golden age.
Well, Matt, radio telescopes.
Radio telescopes is the big one. And they can measure much further out, so they can see the spinning gas of galaxies as well as the stars. So you can measure the speed of this rotating gas, which goes much further out. And this just adds more and more evidence that there is this that the weight of these galaxies, the spin just isn't right. If you were just to have Keplean motion or using Newton's laws, there just isn't enough mass to allow the spins of these galaxies to be the way they are without all the stars just spinning off out into space. It's a bit like a merry-go-round going too fast, and the kids all falling off it. There's some mass holding them in. Right. It's like the kids are strapped into the merry-go-round by dark matter.
That sounds like a really dark movie.
The kids are strapped in with dark matter.
On the merry-go-round.
And there's a clown in the middle making it go faster and faster.
Catch it soon on Netflix.
But then this isn't the only line of evidence, these velocities of stars, because you could actually start ruling that out by having a modified theory of gravity, of which there are a few, like Mond and things like that. But let's move away from that for a second, because gravitational lensing also is really obvious. So sometimes you see the light from stars being bent by objects that just simply aren't there.
Yeah.
So there must be dark matter there, because the light's being bent around something that's very, very massive but not visible.
Right.
Just in the same way that Einstein was proved correct by stars appearing behind the sun during solar eclipses, it's the same thing. There's dark matter that's doing exactly the same as that. And then distribution of gas in galaxies, the variations of the pattern in the CMB. If you remember, if you go back to podcast 123...
Classic.
It is a classic. I love that one because it talks about baryonic acoustic oscillations. And that, for me, is one of triumphs of cosmology. I think the people that look into all that stuff are so radically creative and clever. It's just amazing. All this evidence basically says, look, there is dark matter out there, and the consensus on top of that is that this dark matter is probably a new subatomic particle. And finding this particle, this new state of matter, is now one of the major goals of physics.
Yes.
So, Jamie, have you ever heard of the phrase baryonic matter?
Well, I have, because I Googled dark matter, and that's what came up.
Baryonic matter, is pretty much what all the stuff is made from, except a few things, like electrons aren't baryonic matter, they're leptons. So baryonic matter is your normal matter in the universe. So dark matter might not be a baryonic matter. It might be something else. And there is a bit of a problem, is that the CMB and a few other things predict a certain amount of matter that should be baryonic matter that should be in the universe. But we don't see that, and that's known as the sort of missing baryonic problem.
That's right.
In the universe. But they think that they have solved that. So I think in 2017, they think that it's in the sort of intergalactic gas, hot gas. They think it's somewhere in there, and and so a lot of evidence is pointing to that. So the missing baryonic problem is different to dark matter. Dark matter is yet another problem on top of the missing actual matter in the universe. It's something else. You know, our Chandra special we did earlier on in the year.
Oh yeah.
Well, we spoke to 3 of the team of the Chandra Space Observatory.
That's right.
and Grant Tremblay, and he pointed out that the bullet cluster that Chandra really analysed in stunning detail is the probably the best evidence of dark matter, but it's also the best evidence that this modified theory of gravity, in other words, maybe gravity gets stronger as you get further out or faster or something like that, that's almost certainly wrong. Because as these 2 galaxy clusters collided, all the matter has interacted with one another. And bizarrely, stars very, very rarely hit each other when galaxies collide. And so nothing's happened, but the hot gas does collide and lots of star formation and stuff like that.
Yes.
But there's this apparent centre of mass of the bullet cluster is displaced a huge distance away from the normal baryonic centre of mass. So you can look at all the stars and they're clumped together somewhere, but the dark matter is being kind of clumped somewhere else because it's been behaving differently, and that would be almost impossible to describe using modified gravity theory. So it kind of rules that out. So it's a really stunning indication that it's not modified gravity, that we're actually looking for a physical object that has mass that we can't really see. So do you want to go through the list of possible candidates, Jamie?
Well, we've got a lovely graphic, haven't we, that we should put up on Instagram.
It's a beautiful picture of what dark matter could be, and then you realise what an absolute stinker of a problem this is.
Oh, God,
so you've got you've got light bosons, which are things like possible axion-like particles, and axions are a theorized particle, fuzzy cold dark matter, stuff like that.
Now we're
talking. Then you've got neutrinos. So neutrinos exist, but maybe there are different versions of the neutrinos that we're not seeing. Neutrinos aren't baryonic matter, but neutrinos stream out of the sun through the Earth in their billions every second.
What about weak scale?
Weak scale. So yes, all stuff like supersymmetry and, you know, all these things that fall out of superstring theory, extra dimensions.
Little Higgs.
Yeah, I love that. And effective field theory. So yeah, that's hyper speculative and very, very hard to test experimentally, as is everything to do with superstring theory. Then you've got simplified models. So it could just be just other particles that we just haven't really thought about.
Don't know about,
Weakly interacting massive particles. I think they're possibly the most likely, the WIMPs, as they're called.
Yes.
There's also GIMPs as well, gravity interacting massive particles. Then you have self-interacting dark matter or superfluid vacuum theory. But some of my favourites are things like these macroscopic scale things, which are things like primordial black holes might be the missing. So if there's many, many more of these tiny sort of atom-sized black holes, then maybe that explains the mass. But in 2017, Hiroki Nikuru et al. Put some real constraints about what the size of these primordial black holes, and there just is no evidence for them at the moment. You've got massive compact halo objects called machos.
Oh.
And they're things like non-primordial black holes or neutron stars, faint old white dwarfs, and maybe brown dwarfs. Maybe there's just tons of these things, and that's the extra mass. And of course, you can't really see them because they're so faint and dying away. But that seems unlikely. And then, of course, there's this modified gravity or MOG, of which MOND and its quantum physics version TEVES, not to be confused with the football player. There's the tensor vector scalar gravity, and entropic gravity as well, which is some form of emergent gravity theory. All of those are candidates. So, Jamie, I've got a question for you before we go on to the thing that blew my mind. Do you think you could have dark matter planets?
Oh, well, I would say probably not. As much as I'd like to.
Yeah, so it doesn't look like you could. And maybe you could have, dark matter asteroids or dark matter comets. And one of the reasons is if you're dark matter, it looks like the only way you can interact with things is through gravity, which means it's very, very hard for you to dissipate your energy. So when you bump into other dark matter and start spinning around with it and things like this, you can't really get rid of the energy, and so you just spin off again. And so it's very difficult to sort of clump together. And it's also hard to clump together because material doesn't just clump together because of gravity, it also clumps together because of these very tiny electromagnetic forces and other forces in nature that are interacting to actually bind the materials. So it's highly unlikely that dark matter sort of clumps together, that it's very, very, nebulous material. 27% of the universe.
Wow.
Whereas your normal baryonic matter is only 5%. And the rest is dark energy, for goodness sake. Which went
68%.
Yes, 68%. Remember, there is an energy mass equivalency, which is what the quote was right at the beginning. There are loads of explanations, but this is the one that I absolutely love, Jamie, and I think you're going to love it too. So 1906, Einstein's Annus Mirabilis. He is the year that he came up with his equation E equals mc squared. And what that showed was that mass and energy are equivalent to one another, that they are one and the same thing. So, and I think one of the most stunning ways of thinking about this, if you get a giant spring, like a tractor spring or something like that, and you squeeze it together, the energy stored, the potential energy in the spring, you can actually measure that the spring has got heavier because of it. So it's actually heavier when it's squeezed together because of this potential energy. And you can also measure, obviously, the most stunning example of this mass to energy is nuclear bombs.
Yes.
A mind-blowing discovery with unbelievable consequences.
Yes.
But Dr. Melvin Vopson of the University of Portsmouth here in the UK has postulated that not only that mass and energy have an equivalence, but really we should be talking about mass-energy information equivalence. So this is basically saying that information is a fundamental building block of the universe. And this is a very, very old idea, and certainly not mind-blowing in that sense. But to say that it might actually have a mass, this is the real kind of big jump in thinking. So if you ignore any so what we talk about in information is ignoring particular features of an event, including the observer and how you observed. This guy called Claude Elwood Shannon is who basically is the absolute godfather, the god of information theory and computers and stuff like this, and how you send data around, which harks back to Kelvin and his cables under the sea and all that. So there's a connection between information and entropy, because say you're flipping a coin, there's only two possible outcomes in a fair coin flip. So that has lower entropy than, say, the outcome of rolling a six-sided die.
Correct.
So the entropy is different, and that contains information, and information and entropy are connected. And this problem was kind of that insight was a really, really good starting point to solve another problem that goes back ages, which is called Maxwell's demon. Have you heard about Maxwell's demon, Jamie?
I have actually, yeah.
Yeah. We may have talked about it on the podcast before,
I think we have.
Yeah, a little demon that sits in between two chambers and can open the door when it sees fast-moving molecules and shut it when there's slow ones.
That's
so
right.
that you get the two chambers, one fills up with hot air and the other fills up with cold air. And that obviously is decreasing the entropy. And by decreasing the entropy, you're violating the second law of thermodynamics. Well, let's go back to Kelvin and Bolt and all that lot, and Joule. So that conundrum has been going on for ages and ages and ages. What Maxwell came up with it, and everyone's been scratching their heads ever since. Now, Shannon gave this first insight about information and entropy. This guy called Laudner had a principle that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computational paths, must be accompanied by a corresponding entropy increase.
Okay.
Maxwell's demon kind of gets solved because the brain of the demon can't have infinite storage, and so it must have to erase bits of information to store the information it requires to shut and open the door. Therefore, it's increasing the entropy, and that is how you get round this decreasing entropy in the Maxwell's demon problem, that the brain of the demon itself is heating up, essentially.
Sweet Lord. Does anyone else need to lie down?
So we know that there's a connection between energy and information and entropy. But Vepsen's theory is basically saying, look, maybe this means that information itself has mass. It's finite and has a quantifiable mass. This might only apply to digital systems, but it might also apply to analog, biological, or even quantum systems as well. So if there's any information in this system, it might have some mass. And of course, this is getting very exciting, yeah?
Big time.
Professor Wheeler, who's one of the greatest physicists of all time.
It from bit.
Yeah, it from bit. That's exactly right, Jamie. He really was obsessed with information, and he really gets down to the point where he says, derives its function, its meaning, its very existence entirely from the apparatus elicited answers to yes or no question, binary choices, bits. So he was just basically saying, yes, that the whole fabric of space-time itself comes down to bits, and bits contain information. They are either yes or no. Everything, in some way, is information, and things like Hawking radiation is really bewildering, because if black holes are evaporating, then maybe you're losing information, and quantum mechanics say you can't lose information. This is how fundamental information theory has become in modern physics. So Vopsen is proposing that a bit of information is not just physical, as already demonstrated, but has a finite and quantifiable mass when it stores information. And he actually goes on to do the maths and says that at room temperature, 300 Kelvin, you have a mass, information has a mass of 30 undecillionths of a gram,
okay,
which is 3.19 times 10 to the minus 38.
Matt,
that's
don't insult our
noughts.
listeners. They all knew that.
Yes. So yes, it's a very, very, very tiny weight, and at the moment, that's simply not measurable.
So how can you test it, Matt? Please tell me.
Well, if you've got a 1 terabyte device, so you've got a terabyte hard drive, wipe it of all its information, so it's got no information on it, and then store a terabyte of information on it. Now, that should, using his new estimates, the estimated mass change should be about a quarter of a yoctogram, which is, as our listeners will know, is 2.5 times 10 to the minus 25 kilograms.
Of course.
So, yes, and you should be able to actually measure that. So he's asking for a grant to actually design the equipment. So at the moment, he's asking for a grant, and it'll be a bit like the LIGO or something like that, where you're where you've got this fantastic piece of equipment, incredibly accurate and sensitive to measure this weight change. But he's saying, if he can prove that he can design an experiment. I mean, this is the great thing about this particular paper, is that he's not only has he postulated his hypothesis, but there genuinely is a way of testing it. And if it's tested and turns out to be true, I mean, this will be one of the most mind-blowing experiments of all time. And so he could then go on to build this facility and then test whether whether the fifth form of matter is indeed information.
Well, I've got a quote from Vopsen. Would you like it?
Yeah, go on, hit me.
Currently, I'm in the process of applying for a small grant, with the main objective of designing such an experiment, followed by calculations to check if detection of these small mass changes is even possible. Assuming the grant is successful and the estimates are positive, then a larger international consortium could be formed to undertake the construction of the instrument. This is not a workbench laboratory experiment. It would most likely be a large and costly facility.
The paper actually finishes with a really interesting little point. And he says,
Here we go.
Assuming that all the missing dark matter is in fact information, the initial estimates indicate that 10 to the 93 bits, that's 10 with 93 zeros, 1 with 93 zeros, 10 to the 93 bits would be sufficient to explain all the missing dark matter in the visible universe. And he says, remarkably, that number is reasonably close to another estimate of the universe information bit content that was given by a chap called Goff, or maybe Koff, or Goff,
Or
Goof, or Goof. In 2008, using an entirely different approach, he got to 1 with 87 noughts. We're only a few orders of magnitude out, so that it's pretty sensational stuff. That there is some hints that it might not just be a complete ludicrous thing.
Jeez, that is insaniac. My mind is blown. Like many of our podcasts, Matt, I might have to go back and listen to that again so I can kind of try and decipher exactly what you were telling me.
Don't you think that would be extraordinary if the whole of the universe was being held together by information?
I mean, that is rather beautiful, don't you think? It's absolutely mind-blowing. Matt, talking of mind-blowing, I've got a space fact for you.
Okay, yes.
The sun is 0.000000006% gold.
It looks gold, doesn't it?
Making it. Do you know what the total mass that means it has of gold, Matt?
Well, I know the sun is heavy, and you didn't give me that many noughts. In fact, how many noughts did you give me? 0.6 of a billionth percent. That's going to be heavy still.
It's really going to be heavy.
Go on, hit me.
Well, I don't even know how to say this number, Matt. You're going to need to help me. 1900 and then 18 zeros.
I mean, we could split it up into millions. 1,900 million kilograms.
My God. How big would the gold chain be that you could make me out of that?
It'd be pretty big. 1,900 billion kilograms. So when it goes supernova, when it all sort of blows off, there's a lot of gold in there, isn't there? You realise that actually, yes, stars generate a lot of stuff. Yeah. I think that gold was there before, so the gold must have come from the nebula that the sun was made from. So it'd already come out of some pulsar that has collapsed and sent out loads of gold into the universe. That is exciting in itself, isn't it, Jamie?
It's just nuts, isn't it?
If people have enjoyed wondering about dark matter, what should they do?
Well, there's only one place to go, and that's www.interplanetary.org.uk. There you will find everything you need.
Oh, that's awesome. And how can they help?
There's only one way you can help us, and that's by becoming a Patreon. And what advantages do you get, Matt?
Well, you get to feel good about yourself, that you're disseminating space stuff out into into the wider world in a fun and informative way, and you might get a mug or a T-shirt.
Might get a mug, yeah.
And you get to join in on our Discord channel if you go sufficiently high up the tiers.
Oh, yes.
And the higher up the tiers, the less tiers you'll have.
Oh, that's beautiful. Well,
Isn't that beautiful?
Matt,
yeah.
I wish you a good weekend, a relaxing one, and we'll see you next week.
Bye-bye, Spodcats. Have a lovely weekend.
See you soon. Bye.